All right, hello everyone. So today we're going to be doing a Calc 1 problem where we're going to find the volume using the washer method of a solid that results when you rotate a region around these three axes here. So set up an integral that represents the volume of a solid obtained by taking the region bounded by y equals x squared plus 1, y equals minus 4x plus 13, and is rotated around one of these three axes. So first of all, let's draw out the picture that we have when we take a look at these two graphs and we graph them. So the straight line, that's minus 4x plus 13 in blue, and the red graph is the x squared plus 1. That's a parabola. So if you graph those, and you just need like a rough sketch here, you get something along these lines. And the region that's bounded by these two graphs is what you see there in orange. And there are two x values here that you need to know in terms of for the setup. And the way you find those is by setting them, the two functions equal to each other, because as the picture shows, that's where they intersect. And if you set them equal to each other, you get a quadratic, move everything over to one side. And if you go ahead and try to solve this, you're gonna go ahead and get two values, minus 6 and 2, and then I'll let you work that out yourself. So I paused the video just in case, but you're gonna need those values as to set up the integral. All right, so let's start with part A. For part A, we're gonna take that region and we're gonna rotate it around the x-axis. And if we did that, we're gonna go ahead and have something along what you see here, okay? And yes, this is a three-dimensional object because the idea is like, take this region and imagine it's on the table, on a table. And when you rotate it around the x-axis, this is the x-axis down here. Yeah, it's gonna come out, kind of think of it as like it's gonna be facing you, and it's gonna go around. It would make like, when it's rotated, it kind of reflects over down here. Oops, when you rotate it, it kind of does this reflection. You have a three-dimensional picture out here. Now, we call it a washer because the volume that results is a result of you taking the volume that would be bounded by those two x values and the minus 4x plus 13, so it'd be like all this stuff. You rotate that, you would get a three-dimensional solid, and you take whatever that is, and then you take the volume that would be under the parabola when you rotate it from minus 6 to 2. You take that, you get a volume as well, and if you subtract those two volumes from each other, that's the volume that you're given here that you're looking for. And a lot of people like to draw these little circles out, and they say, look, think of this big circle as what you get when you rotate that line about the x-axis, the minus 4x plus 13, and take this little circle right here, and that kind of represents the rotation you get when you take that parabola and you rotate it around the x-axis. And you have that gap in the middle, and people think, oh, it looks like a washer, you know, one of those things that you use to like fasten a bolt or something. So that's why we call that the washer method. And this is a three-dimensional object. You probably heard, sorry to repeat that again and again. Now, I don't stress the drawing here because you don't really need to know how this looks like technically speaking, but I like to, myself personally, like to know what I'm looking at. But the problem is I can't draw at all in three dimensions, so the best I can do for you is something along these lines. This is what you would have, and it kind of looks like some kind of vase in a way. That's got like a gap in the middle, okay, or something along the lines. Yeah, just think of it's got a little there's a bit of solid stuff on the outside, but it's got a big hollow part in the middle, and that's the whole idea. One of the big differences between using the washers, and maybe you heard of the disc method, and we have a video about that as well. The disk method basically works with you taking a region, you're rotating, you get something solid. A washer works when you're working with a region you're rotating and you get like a hole or a gap, okay? Now, how do I go about in setting these up? We have this equation right here, which is volume equals pi times the integral that goes from a to b, OR squared minus IR squared dx or dy. Now, what is R and what is IR? OR stands for the outer radius, and the outer radius is the distance from the axis of rotation to the function farthest to the axis of rotation. And then we have I sub r, which is the inner radius, which is the distance from the axis of rotation to the function closest to the axis of rotation, excuse me. And I write this in this particular way because many books will, and teachers as well, they write f of x squared minus g of x squared, something along those lines instead of what I wrote here. Because they're like, yeah, you're essentially working with two functions and you're subtracting their volumes, which is true. However, the reason I don't do this and write this notation out is because this idea is like a generalization, basically, of what books say or teachers say in terms of two functions and finding their volumes and subtracting them. And the thing is, the other thing is that the reason I write it this way is because I don't like the notation that is used when you use f of x and g of x squared, because excuse me, people just think of the two functions that are given and you're going to be always subtracting them. In some reason, I've noticed that. But there's always, depending on the axis of rotation here, apologies, or maybe it's allergies, I don't know. It's not always just going to be the difference between these two functions that you're subtracting. So that's why I prefer to look at it this way. All right, so let's, find out what we mean by the outer radius and inner radius in this particular problem. So in our case, the outer radius would be, this over here, would be minus 4x plus 13. Because the axis of rotation is the x-axis right here. And what's the function that's farthest from the axis of rotation, that's bounding this region? It's the minus 4x plus 13. So the whole distance is, well, it's just this vertical distance, that's minus 4x plus 13. And what's the inner radius, I sub r? That would be the parabola, x squared plus 1. Because the distance from the axis of rotation to the function that's closest to the axis of rotation, which is x squared plus 1, is x squared plus 1. So our setup for us here would be volume equals pi times the integral that goes from minus 6 to 2 of minus 4x plus 13 squared minus x squared plus 1 squared dx. And that is it. That would be our setup. Okay, so that is our volume. Now, I don't really care too much about the actual computation of this. I'm not saying this is a fairly straight integral, but all you would really need to do here is FOIL out minus 4x plus 13 squared, and as well as x squared plus 1 squared. FOIL or expand those out and collect like terms, and then find the integral of this using the fundamental theorem of calculus and working with polynomials, so it's not too bad. So not really what we care about here. It's really getting the setup, and that's really the hardest part. Now, the next setup here would be around the axis y equals minus 1. So what's my outer radius? Well, the outer radius would be the distance from the axis of rotation, minus 1, to the function that's farthest from that. So that'd be minus 4x plus 13 plus 1, or minus 4x plus 14. Why is that? Because this distance from the line to the x-axis, well, that's what y is equal to. That's minus 4x 13. But then, see, you have this additional distance. That's another 1 unit. So we're adding 1, so it's minus 4x plus 13. And for the inner radius, it's it's x squared plus 1 plus 1, because x squared plus 1 is this distance, and another 1 unit, that's x squared plus 2. Yeah, and again, it's the inner radius is the axis, it's the the radius, the distance from the function that's the closest to the axis of rotation. So that's x squared plus 1, but the whole distance is that x squared plus 1 plus 1, okay? And our setup would basically be the same in the sense of the two values, minus 6 to 2, minus 4x plus 14 squared minus x squared plus 2 squared dx. And sorry, I'm getting a little sloppy here. And the last one is when we're rotating around the line y equals 40. So if you rotate it, you get like a picture that you see here. Sorry, I didn't do that when you rotate around y equals -1. You don't really need to find the picture, but just did it here anyways. So what is our O sub r and our I sub r here? And yeah, you have all of these would produce gaps when you rotate, when you do the rotation. So the distance from the axis of rotation, 40, to the function that's farthest is all of this right here. That's my distance. And that would be 40 minus x squared plus 1. Right? X squared plus 1 is now the function that's the farthest from the axis of rotation. But what is that distance? Well, that distance would be, well, that line, but we get that from taking the, let's choose blue here, taking this whole distance, which is 40 units, minus this distance, which is x squared plus 1, and if you subtract that together, that's how you get that, okay? And in other words, for us, that would be like 39 minus x squared. And likewise, 40 minus negative 4x plus 13 would give me 27 plus 4x. That is my inner radius, okay? All right, so that is what you would have for your inner and your outer radius. And you would just set up your integral again from minus 6 to 2, you have a pi. And this would be 39 minus x squared squared minus 27 plus 4x all squared dx. And last but not least, it's dx whenever you're rotating around something that's around the x-axis or parallel to the x-axis using the washer method, it's dx. And anything that when you rotate around the y-axis or it's parallel to the y-axis, so lines like x equals 7, x equals -1, x equals any constant really, those are always parallel to the y-axis. That's where you would switch to dy, and these would be functions of y. Okay. All right, well, I hope this helps. Thanks for your time. Appreciate it.